2 days ago, which you can watch online. I'm going to concentrate on one thing we did, and I'm going to do it in some detail. I'm also not going to talk much about data. I'm going to talk about models. So, decision making on future landscape. Landscape decision making is complex. It's a problem that makes climate look easy. It involves an awful lot of disciplines: ecology, economics, climate science, social science, and lots that I've missed out there, and don't be upset because I've missed you out. Okay? Each has their own models, their data, their expertise that we have to synthesize before we can make those decisions. Now, I've got half an hour, and I don't have time to deal with all that detail and complexity. And I'm a mathematician, so I'm going to abstract the problem down to something much simpler, and I'm going to talk about a single uncertain model and making one decision. But that doesn't mean we can't do the detail. It's just that the detail gets in the way of the simple story I'm trying to tell. Okay? You'll see we have plans to do the detail later. So we're making decisions about the unknown future using uncertain data with imperfect models. What could possibly go wrong? You know, this is, in some sense, this is an impossible task, but it's a task we have to do. And let's go about seeing how we can use models to inform decision makers to make decisions. So the first thing when you're using a model, everyone knows the quote from George Box: all models are wrong, some models are useful. There's another really good quote he came up with, which is: scientists are like artists, they have an unfortunate tendency to fall in love with their models. The model is not reality. Models are a mathematical description of reality, and they're all wrong. And I hate to break that to some people. Sometimes they get quite upset. But it's true. And we have to take that into account. And if we don't take into account, we can get very misleading results. So let's look at how decision making, or how models are classically used to inform decision making. And the sort of classical approach to this is scenario analysis. So we investigate a number of scenarios, possible futures, and often these are done in great detail. And I'm going to use as an example the Climate Model Into Comparison project, which is used by the IPCC. I'm not picking on the IPCC, it's just an example that's out there, and it's a nice one to talk about. So what the IPCC do, or CMIP for the IPCC, is they have 4 future scenarios of basically greenhouse gas concentration. It's usually talked about CO2, but it actually includes other greenhouse gases. And they have these representative concentration pathways, and there are 4 of them. And those are worked out with a huge amount of effort from climate scientists, social scientists, of what a possible future could look like. So those are the 4 things, and they take years of effort to produce those. So each of those curves is one of the scenarios. And I say they take huge amounts of effort, but being a mathematician, we can actually describe all of those with 5 numbers. And you'll see a fit in a minute where we just put a spline function through them, and you can fit them all with just 5 numbers. They're not very nonlinear. And CMIP then runs a variety of climate models for each of those scenarios. Now, the one thing we can be certain about the future is it's not going to be one of those scenarios. So here's the results of plotting it from the IPCC report, and they plot the trajectory for 2, and these are the spread across the models for each of the scenarios. So there's a spread across the different models that are run. There are 32 models here, 39 models here, and this is just the spread across the models. But what if I'm interested in that point there, which is pretty much 1.5 degrees, which is what came out of Paris, and I think actually shocked the climate community because they hadn't looked. There isn't a scenario that low. And this, I think, is illustrating the problem with scenarios. Once you move away from the particular scenarios, you have no information about what's going on. So you can't jump to a new point. You could try to interpolate or extrapolate those scenario pictures, and because I can express these things in terms of 5 numbers, I can now generate possible concentration pathways. None of these have got storylines, but they're all feasible things that fit within. I bounded by those 2. Oh no, I put an extra one in there. They could go down to 1.5. But I just generated those very quickly on the computer, and I could interpolate them. But it's frowned upon because we don't have the storylines. We're breaking the sort of reason for the scenarios. And it also would be very difficult. We've looked into doing this, and it really is very hard interpolating the results from the climate models to get to those hundreds of pathways I've drawn there. And these include overshoots, and they, oops. These include overshoots and some weird structure. So scenarios are not very good as a decision support tool. They're fine. When CMIP started, it was designed to compare the different climate models, and this is a great tool for that. It's not a great tool for decision support. So what are the alternatives to using scenarios that we could think of? Well, the one that's commonly used particularly by economists, is optimization. Let's find the model inputs which optimize some output. Or rephrasing that model inputs, you can think of those as policy levers. What policy levers do I pull to get to some best outcome? So my best outcome might be, I want to limit changing global temperature to 1.5 degrees. What are the 5 numbers that I can put in to do that in the best way? And I could say I want to do that, to limit that to in the best way and the cheapest way. Now, this is much better for decision support for scenarios because you're concentrating on the decision. You're actually saying, what do I have to do? What decision do I have to make to get an output that I want? That's good. Concentrates on the decision, but every mathematician knows optimization is a hard problem. Optimization of a deterministic function is a hard problem. Optimization under uncertainty is even harder. And this assumes there's only a single best set of inputs. There's one position of the levers that gives me the answer, that gives me the decision. And that's not likely to be very robust, so if the problem changes, and my experience is problems always change, we've probably not got the right answer. We've not got that optimum anymore. And it leaves the decision maker no freedom to make a decision. It says, this is the decision you have to make. Or this is the decision the model says you have to make. And then the decision maker's, yeah, but, and then the model isn't helping anymore. And if it's hard to optimize under uncertainty, it's almost impossible to optimize under discrepancy. We don't know how bad the model is. Model discrepancy is the unknown unknowns. If we knew what the problem was, we'd fix it. So let's just step back a little and think about other ways we could tackle this problem. So in scenario modeling and optimization, we run the model forwards. We say, these are my inputs, these are my levers of policy. What does that give me as an output? So I have to have some equations. You have y equals some function of x. So this is the output, and these are my decision relevant inputs. But we can also, in theory, run the model backwards. We could just say, I've got what inputs would generate the output. Okay? So you can get the inputs in terms of the outputs. I'm going to stress the in theory thing down here. At least in principle, you can do that. As a mathematician, I can write that down and probably just forget the rest. But I'm not going to. I'm not that sort of mathematician. So let's see if we can use those ideas of inverse modeling to help decision makers make decisions. And this is a lovely phrase that Danny came up with, post-optimization decision making. So we're not going to optimize, we're not going to use scenarios, we're going to use inverse modeling. So we get the decision maker to specify what outcomes they would like. This is not a single outcome, this is not what's the optimum, what's the best thing that could happen. This is, what outcomes could you live with? What outcomes wouldn't be a disaster? And then we could use the inverse model to map back from those acceptable outcomes to see what the acceptable decisions are. So what decisions can we make to get to the outcomes we'd like? And we can use that with the inverse model. So for the climate example, we might say we want global mean temperature to be less than 1.5 degrees. Anywhere less than 1.5 degrees is good. And find all the CO2 pathways that would get us there. And then the decision maker can say, well, I don't like that one, I don't like this one, I'm going to choose that one. Now comes the hard part. You now have to build an inverse for your model. And building inverse models is, in that wonderful mathematical phrase, non-trivial. So usually people do this using adjoints, and there are these things called automatic adjoint compilers that are supposed to do this for you. At this point I was going to say that I did this once, but I didn't. I got a PhD student to do this once, and it was the bane of her life. These things are awful. It's a very messy business. You're basically taking code and differentiating it. You don't want to do that. But I think we have methods that enable you to not have to do that. So if you move forward models fast enough, then I can just map out the model space, the f of x, everywhere, and work out what the inverses are just by going and plotting everywhere. So if my model's really fast, I don't have to worry about producing the inverse. What if my model's not really fast, and most of our models are not really fast? So what we can use then are things called emulators. And there's an awful lot of work being done in the last 10, 20 years on emulating large complex numerical models. And an emulator is a fast surrogate model, but it gives you an estimate of its own uncertainty. So it tells you how well it's doing. And that's really important because it says, because you're using the emulator, you've made the uncertainty this much bigger. And then I can take that into account. And I can, if that uncertainty gets too big, I can put a bit more time into building a better emulator. Now, one of the things we use emulators for is this thing called history matching. And if you came to the first workshop, you'd have heard Danny talk about history matching. So with history matching, we have some data, and we want to calibrate the model. We want to fit the model to the data. And again, we don't want to optimize because it's difficult, and we're lazy. So history matching uses a scale distance between the data and the model prediction. And it says if you're too far from the data on that scale distance, that's implausible. You couldn't have got the model, you couldn't have got the data from that set of inputs, so you can just wipe those out. They're not of any interest. And you then refocus down on the bit you haven't ruled out yet, improve everything, do the same process, and you're now cutting out more, and you keep shrinking down until we find a very small part of space where the model inputs could have given the data. And that's history matching. That's how we use to calibrate models. We can do the same thing with our model outcomes rather than data. So now, instead of wanting to know what model inputs are compatible with the data, we want to know what model inputs are compatible with the outcomes of the decision we want. So what decisions are compatible with the outcomes we're looking for? Discrepancy is not a problem. It's built into history matching from the ground up. It was designed to cope with discrepancy, so that's not a problem. Uncertainty is not a problem. It's not a problem. Now, if you optimize, you always get a best fit, even if it's way off where you really want to be. So the optimizer will give you a decision even if that decision is actually one you don't want. The outcome is one you don't want. History matching doesn't do that. What history matching does, if it can't find a solution, it tells you there are no solutions. There are no decisions that would give you the outcomes that you want. You really are in a no-win situation. You cannot get there. In which case you need to go back and rethink the problem. And you might say, well, okay, it's the model discrepancy that's the problem here. This model isn't very good. We just can't get there. Or it might be that, you know, that old joke, you don't want to start from here. But it's good to know that, if you're a decision maker, that this problem is just not going to work. So I have skimmed over the detail. I said I wasn't going to talk about detail. This is a slide from Danny on the expression of interest he's put in for the project. And this is an attempt to do this for landscape decision making. Or, no, it's not a big enough project to do it for landscape decision making, to show it could be done for landscape decision making. And again, I'm going to jump over that because I'm not going to talk about all the I'm just going to do a quick summary of what we've talked about. So scenario analysis. Here are inputs, our decision variables. Here are outcomes. We have a limited number of formal forward model runs. It's not helpful for decision support. It really doesn't give the decision maker what they want. And because there's absolutely no information about what happens when you get away from those scenarios. Optimization is better, it examines all options, but it's hard. It's difficult to include discrepancy and uncertainty. Doesn't give you a range of options, and it's almost certainly optimizing the wrong problem. These problems change, they're hard to set up. It does at least give the decision maker some information, but it probably doesn't give them enough. And then the inverse modeling idea, where we specify a range of good outcomes, and that we track back to get the special, what are the decision variables we need to do that. It requires fast models or emulators. We can't do this on straight climate models. We'd have to build emulators of climate models, for instance. But it gives you a nice range of options, all of which give good, in inverted commas, outcomes. And it allows the decision maker to include the additional things that aren't in the models. We had a long discussions at the beginning of the program about immeasurable things. If the model says we have to plant trees all over the Lake District, then I think the Wordsworth Society would probably get a bit upset. That's an immeasurable thing. It's very hard to put that into numbers. But decision makers have to take those into account. External things that are not in the model. It might also have come up with surprises. I should have drawn this slightly different. There may be another set of good inputs down here we never really thought about. But they still give you the outputs that you're looking for. So, conclusions. One of the things we've done this month is come up with this new method for how we might use numerical models to help in decision support. Based on the idea of inverse modeling, gives a range of good decisions, and it gives the decision makers choice. The decision makers actually have a part to play in this. It's not just an optimization. This is what you have to do. It's within this range, this is what the model says are good decisions. And I think this could be useful not only in landscape decision making, but I think landscape decision making is a good example because it's really complex. There are lots of things that are probably not modeled that you need to include in the decision. Okay, thank you very much.